uh, the discussion on convolutional neural network. So in our last class, we have already discussed about that is the convolution layer, convolution operation. And in this lecture, we will discuss a full convolutional neural network. Let's say we want to build up a convolutional neural network for object classification, or maybe you can say uh, image recognition. So maybe we have several images of different animals and objects, and we want to classify those objects or images. Like this is an image of a cat, and we want a classifier that can recognize maybe the image of a cat. So for that case, what we have to do, we have to develop a convolutional neural network, and then utilizing a large volume of images of cats and dogs and different other objects, we want to train this convolutional neural network, and then we will test utilizing different sets of images. Like we can see this is a cat, but sometimes we may feed this network to a black cat. Maybe this convolutional neural network can also recognize that the black cat also. Okay. So for that, different, maybe we can say we can train this model utilizing 1 million of images, or maybe 10,000 of images, and then it will learn how to classify, how to recognize, how to detect different animals and objects. So our target is that. Okay, and for that, a simplistic convolutional neural network can be this one. Okay, so this is a simplistic convolutional neural network. What we have to do, it has the dimension. Okay, like we can say maybe this one 128. Okay, 128 by 128 pixels image, and then we can convert this one as our grayscale image, or maybe we can also read this RGB image, or you can say this color image. So if we read this color image, then we will get three components, that is R, G, and B. For R component, we will get a matrix of different colors, R component of different colors of this image, and we will get another matrix for the G component, the color component, and we will get another matrix for B component. Okay, B component. So if we consider this one as a color image, otherwise, if we convert this one as a grayscale image, then we will get just only one matrix. Okay, only one matrix. The grayscale values, those color values we will get from 0 to 255. For each and every pixel will represent within 0 to 255 number. Okay. So for the grayscale image, for the color image, we will get three different metrics. Okay, now this will be the input, and then at first what we have to do, we have to add a convolution layer. So you have to add a convolution layer. So this convolution layer, we can design differently. Okay, we can design this convolution layer differently. Like, think about a convolution layer. In this case, we can think about a convolution, that is, this is the convolution layer, 2D for 2D convolution. And in this layer, we will think about 3 by 3 filters. Okay? In convolution operation, we have to think about the filter, or you can say kernel. So here 3 by 3 kernel we can add, and we can think about like 25 kernels for that. So that means this convolution layer. So this convolution layer, it can be 3 by 3. So we can utilize 3 by 3 kernel. And how many kernels we consider? 25 kernels. 25 kernels. The 25 3 by 3 kernels we can consider for this convolution. Then what it will do, as I have already mentioned, that is the this one is one of the 3 by 3 filter. Okay, so 3 by 3 filter, just only one filter, and this is our image. But for the image of our cat, it will be 128 by 128. The size of the image will be 128 by 128. Okay, so this one will be the image size 128 128, and the filter size or kernel size is 3 by 3. This is filter 1. Similarly, we can consider filter 2, filter 3, up to 25 filters we can consider for the first convolution layer. Okay, so here in this convolution layer, we can consider 25 filters, and each and every filter size is 3 by 3. And this convolution layer we can add just using this code. Okay, that is our convolution layer here. Model add, and convolution 2D. So we can add the convolution 2D convolution of this size. Okay, 3 by 3 filters, and 3 by 3 filter size of 25 filters. And here input shape, that means our image input shape, it is mentioned 28 by 28, but in our case, it is 128 by 128. 128 by 128. And then it is mentioned 1, that means this is the grayscale image. Okay, 1 means the grayscale image. Grayscale image. If we think about 3 here, if we just place here 3, that means it's a RGB. Okay, RGB image. So this will be the first convolution. So after the convolution, we can add a pooling layer. Pooling is subsampling. Pooling is our subsampling. And for the pooling or subsampling, what it will do actually? The pooling or subsampling, it will reduce the dimension of our feature maps. Each and every filter will generate the feature maps. Like filter 1 will generate this feature map. Okay? It will generate this feature map. We have already seen in our last class. That is you can see it here. Okay, so this is filter 1, and this is our image, 6 by 6 image with a straight 1. So this is our first feature map. Okay? This is our first feature. And then filter 2 we have utilized to the same image, and then we got another feature map. Okay, so the first feature map is 3, -1, -3, -1, -3, 1, 0, so -3. These are our the feature maps, first feature map. So here is the same. Okay, that means this is filter 1, and in our convolutional layer, we have utilized, or we have performed the convolution operation, and after that we got this. This is the feature map 1. The feature map 1, first feature map. First feature map, that is the feature map 1. And this is the second feature map 2. So when we utilize this filter number 2, and apply the convolution operation in our image 6 by 6 image, then we got this feature map Okay, we got this feature. Now we want to apply the pooling operation. Pooling operation. We want to perform the pooling. There are several types of pooling, like the max pooling, mean pooling, average pooling. Okay, so here, if we want to apply the max pooling, then at first we need to determine uh, the there is the pooling kernel size. So let's say the pooling kernel size is 2 by 2, and also a straight, the pooling a straight for the field. Let's say a straight is 2. So if we consider this, there is the 2 by 2 and a straight equal to. So that means this feature map, we have to uh, split this one or divide this one in 2 by 2 window. So here, this is our 2 by 2 window or 2 by 2 patch. Okay, so this is 2 by 2 and this is 2 by 2. The feature map 2 by 2. So this is our kernel size or filter size for our pooling, 2 by 2. So here is 2 by 2. That means we have to divide these feature maps into 2 by 2 window. So this is 2 by 2 patch. And then as this one is the max pooling, so on this patch, on this 2 by 2 region, we have to find out the maximum number. The max pooling means max is maximum. So here the maximum number. So that means if we try to find out the maximum of this 4, the maximum is 3 here. Okay? So maximum is 3. Here is the 3. Maximum is 3. Then straight 2, that means we have to shift the window 2 bits. If we shift this window 2 bits, that means we can see 1, 2. So here is again new window. It will start new window, and again it will select 2 by 2 patch. So this is the 2 by 2 patch. Okay. And again, in this 2 by 2 patch, we have to find out the maximum. So you can see the maximum value for this one, it is 0. For this passive 0. Then we have to think about the next. We have to again shift down. Again, for that case, the straight is 2. So 2, that means we have to shift 2 rows. So now the new 2 by 2 window, 2 by 2 patch will be this one. And we have to find out the maximum because we are trying to utilize max pooling. So here maximum is 3. Maximum is 3. And then shift right, then we will get this one. And the maximum value in this region is just only 1. So here is 1. So that means in feature map 1, if we apply 2 by 2 filters and straight equal to max pooling operation, then the output size will be this. That is 3, 0 and 3, 1. So this one will be the output of pooling operation utilizing this kernel. Utilizing this kernel. Similarly, we have another feature map. So this is the feature map 2. We can apply again the max pooling here. Utilizing the same filter. The same filter here is a 2 by 2 and a straight equal to. That means this is the first patch. And what will be the maximum value for the there is, you can see -1, -1, -1, -1. All these are negative. So maximum is actually negative. Okay? So that means -1. And then shift 2 bit, then we will get another 2 by 2 window. So here the maximum is 1. So that means this is the 1. Then shift down the 2 by 2. This is 2 by 2 and maximum is 0. So here it will be 0. And again the another one is this one. Okay. So here is negative. So maximum is 3. This is 3. Okay. So this one will be the output of pooling operation on our feature map 2 utilizing the filter 2x2 filter of a straight 2. So this one will be the output of our pooling operation. We have applied the max pooling. Similarly, you can consider about the mean pooling. So mean is just minimum value, or maybe average pooling. Find out the average of these 4 values. Okay, in that case, find out the average of these 4 values, and then we will get the feature map. But these feature maps are reduced in size. So reduced in size. So the pooling operation is actually from the feature map. It will reduce the size of our feature map. So here is the max pooling. Max pooling. If we want to just apply the max pooling, so what will be the code for that? Here we can see there is after conclusion. If we want to apply the max pooling, so here is the model2.add pooling 2D, and we can see this is our 2x2 filter. Okay, so 2x2 filter. So that means in this pooling we have applied the 2x2 filter. So after that, again we can see again we have the convolution operation. So again have the convolution operation. And for this convolution, again we have to think about that is our filter size and also how many filters you want here. So let's say this time the filter size we can consider the 3x3 filters. But how many filters we want to add here? Let's say 50 filters. Okay? 50 filters in the second convolution layer. So here for the coding, you have to write just model2.add convolution 2D. As the 50 is the number of filters and the size of the filter is 3x3. Okay, then we will have this convolution layer, the second convolution layer. Then again, we want to apply the max pooling. And for that, we have to define the filter size. Okay, so model2.add. Now we have to add the pooling layer of 2D, the 2D pooling, and here is our filter size is 2x2. So then we will get this pooling layer. Okay, this pooling layer. Okay. So we can see there is we have added the convolution layer, and in this case we have added 50 filters of 3x3 size, and then we have applied the pooling, and we have utilized the 2x2 filters. Okay, for this pooling. Okay, now what we have to do next after this pooling layer, we want to flatten. Okay, we want to flatten. So that means we have to convert the feature maps to a one-dimensional vector. One-dimensional vector that is called the flattening. So to convert these feature maps, so each and every feature map is the feature. Feature map is actually the features. They consist of features, but we want to make it one-dimensional. So for that case, we have to add the flatten layer. Okay? Flatten layer. Then how can we add the flatten layer? It's simple. We need to apply the flatten. Okay? The flatten. So yeah, so here is model2.add, then just flatten. It means now we have to just make the features in one dimension. Make the features in one dimension. So that means we can see that after this pooling layer, we will get the feature maps, and after that, if we flatten, then it will be one-dimensional vector. One-dimensional vector. Why we need the one-dimensional vector? Now actually we want to add the neural network. It is called the fully connected neural network for classification, because already we have extracted the features utilizing the convolution and pooling. So we have extracted the features from the input, that means from the image of the cat. We have extracted the features. So, and then features we have flattened, that means we have converted those features into a vector that is called the feature vector. So we have a feature vector now. So this is feature vector. The size of the feature vector will be 1250. Okay, so feature vector. Now, if we have a feature vector, what we need now a classifier. Okay, a classifier. So neural network is a classifier. Now we can add a neural network, and for that, we build here a neural network. This is called fully connected feed-forward network. Fully connected feed-forward network, because in deep neural network architecture, usually each layer of nodes are connected to the next layer. So the fully connected. Okay? That's why it's called fully connected. And for that, we can see here at first, we can say model 2.add a dense, that is a dense neural network, and output dimension is 100. That means here is the input size will be 1250. Okay, the input size, number of neurons in our input layer, it will be 1250. And that is our dimension of our vector. So the one dimensional vector. So in one dimensional vector, we have total how many elements are there? 1250. 1250. So that's why in input layer, how many neurons we have to add? We have to add 1250. But the next is the hidden layer. Okay, then how many uh, neurons we need to add in hidden layer? So here we design this neural network as we will add a dense layer, that is a hidden layer of our dimension 100. Okay? Dimension 100. So that means 100 neurons in our hidden layer, that is fast hidden layer. And then we have to apply the activation function. Okay, that we can apply the activation function. Here is the activation. Activation is here we have utilized the relief of activation. Okay? You can apply the sigmoid or maybe 10H activation. Then after that, we have add another dense layer, and then the dimension of the dense layer is 10. Dimension of the dense layer is 10. And then we have add again the activation, and this time the softmax activation. So it means that the last layer we have added, this one is actually our output layer. The number of neurons in the output layer is 10. Okay, number of neurons in the output layer is 10. And the activation function we have utilized, that is called the softmax activation function. Okay? Softmax activation function. So it will just provide us the probabilistic result. Okay. So that's the completion of our convolutional neural network design. Okay. So that's the completion. That means at first we have added the convolution layer and defined the input step, input size, and define whether it is colored or maybe the grayscale. And then we have added the pooling layer. And then again we have added the convolution layer. Again we have added the pooling layer. And after that we just flattening our feature maps to one-dimensional vector. And after that we have added a neural network. And for that neural network, the hidden layer, we have just added one hidden layer. And then hidden layer, in that hidden layer, we have added 100 neurons. And then activation function we have used, there is our real activation, and then we have added the output layer. And in output layer, we have added just 10 neurons, considering the 10 class of objects or animals we have. And then after that, we have added the softmax activation. Okay, so the softmax activation will provide us the probabilistic result. So this is the completion of our CNN design, or convolutional neural network design for the animal classification or object classification. Okay, now what we have to do, we have to know a few things. So why subsampling or pooling will work? Specifically, as we can see that the subsampling, if we consider that this is the feature map we have, 128 by 128, then if we subsample, maybe convert it like 28 and 28 pixels but still we can see there is the structure of the bird we can observe. Okay, so even though the size we are reducing, but still most of the features or most of the pixels are uh, not distorted. Okay, we can see it is now as it is in our original image. So that's why subsampling will reduce the number of connections or number of uh, parameters to learn, but at a time it will also hold the originality of our actual image. So that's why subsampling will work. But one thing you need to remember that is for the case of our image, uh, maybe the subsampling will work better, but for some cases we should use the pooling. So for that case, the subsampling or pooling, you will see that the convolutional neural network is designed uh, for our natural language processing. But in many cases, you will see that there is no pooling layer. Why? Because if we lose just one character from a word, so the word will change. Okay, but if we just remove one pixel from this image, so nothing will happen. Okay, so that's why the subsampling or pooling, specifically we need to carefully add this layer, because in some cases maybe if we lose some information, that will be that will be effect more on the output. Okay, so we have already discussed this. Okay, so here is an example for that. Actually, we can see I have already written here. After applying the max pooling on this feature map 1, the output is this one. Okay? This one is 3031. And after applying the feature map, there is pooling in our second feature map, the output is this one. So if we consider that, okay, these, and after that we want to apply the flattening, then what will happen? So after that, if we apply the flattening, so after flattening, what we will get? So these feature maps will be converted to a one-dimensional vector. Okay, so one-dimensional vector. It means here is the 3031. So it will written as like this, one-dimensional vector. The first feature map, it will be from the first feature map we will get 3, then maybe 0, then 3, then 1. From the first feature map we will get these 4 values, and then from the second feature map we will get -1. So -1, and then 1, and then 0, and then 3. So after flattening, we will get this one-dimensional vector. This is the one-dimensional vector. One-dimensional vector. So that means how many components will be there? So this is 2 by 2. This is 2 by 2. So this is 2 by 2 means 4 components. This is 2 by 2 means 4 components. So total 8 components we will get. So here is, as you can see, in one-dimensional, we will get there is just 8 components. So that's what it is written. So here is this 3013 and 91103, and then this is the flattening. Then what we have to do after flattening, we have to use a classifier. Okay, so this is the neural network classifier. Neural network classifier we have added. So in this network classifier, we can see that is how to design this one, this neural network classifier. So at first we need to know how many the dimension of our vector, that is this is one-dimensional vector. So one dimension, how many components are there? 1, 2, 3, 4, 5, 6, 7, 8. That means in our fully connected neural network, we have to add 8 neurons initially. Okay? So that means in initial layer, 8 neurons, because the size of this vector is 8. So input layer, we have to add 8 neurons. And then the output, we have to design the output layer. Again, consider that for this model, we want to classify just 4 classes of animals. Okay? So if we have the 4 class of animals, then in output layer, we have to think about 4 neurons. And then the rest of the there is the middle layers or hidden layers, we have to design, that is based on the data set and based on the users. Okay, so there is no a straightforward rule for that. So you can think about, okay, 10 neurons in first hidden layer, and we can add another hidden layer of 10 neurons. We can add another hidden layer of 10 neurons. Okay, so this is user defined. Okay, this part is user defined. So several user can design this part differently. Okay, and after that, the output layer. Okay, output layer. One thing I need to mention here. Okay, so specifically this fully connected neural network is our classifier here. So classifier, that means it will classify something. Up to this one is our features. Up to this one, that is after flattening the one-dimensional vector, this is actually the feature vector. So these are the features. So now the classifier, this classifier can be changed. That means instead of fully connected neural network, someone can think about other classifiers like, okay, I don't want this. I want to use the decision tree. Okay, so instead of this neural network, someone can think about the decision tree classifier, add the decision tree classifier, or maybe support vector machine classifier, or maybe extreme gradient boosting classifier, so, or maybe logistic regression classifier. Okay, so that means this fully connected neural network, this one is the classifier. Actually, we can change it to different classifiers. Okay, no need to. This is actually not necessary that all the time we want to use this fully connected feed-forward network. Now, we want to find out that is the size of the feature map after convolution and after max pooling. So this is necessary. Why? Because to design the next layer convolution network, we need that. Okay, so that means so what will be the output size of this convolution, and what will be the output size of this pooling? What will be the output size of this convolution? And what will be the output size of this pooling? And for that, we have to understand few more things here. That is how to determine the output size of convolution layer. Convolution layer. So convolution layer, we have specifically other than the filter and our image size. Okay, our image size. So as we know that the convolution operation is actually the multiplication and integration of two functions. Okay, one is our filter, that is f, and our image may be g. Okay, so this. So these two functions. Now, in addition to these two, we have few extra things we need to know. That is the straight. I think we already heard about this. The straight. That means we can say that how many bits we want to shift. Okay, so that is a straight. A straight. We can define a state equal 1 or a state equal 2 or maybe a state equal 3. And another thing is padding. Okay, another thing is padding. So that means in our last lecture, I have already shown that is how padding works. Okay, padding, how padding works. That means in our G, that means we can say in our image, when we apply the feature, if our our pass, that is the pass size in our pass, or you can say window, we need maybe some additional layer or additional row. Then in additional row, we can fill this row with the 0. Okay, so this is called the padding. Okay, so this we fill the extra row or extra rows with zeros. Okay, so this is called the zero padding. So that's why sometimes we can use the padding, or sometimes we may not use the padding. Okay, so that's why here is the padding and straight. These are two extra parameters we need to consider in conclusion there. Okay, so the padding can be, here we can say it can be same, it can be valid, it can be full. So 3 types of options we have: the same, valid, and full. And the straight, it can be maybe a straight, that is the number of bits we want to shift. It can be 1, 2, 3, any values. Okay, so now if the same, what does it mean? The padding is same. So it means that add 0 padding to the image to have the output of the same size as the image. So if the image size, the image is G in this case, the image size is M by M. M by M. So this is the image size. Like we consider our image size is 6 by 6. Consider this one 6 by 6. Okay. So that means image size is 6 by 6. And after convolution operation, we want to fix the feature maps also. And the size of the feature map we want to keep 6 by 6. We want to keep the size of the feature map 6 by 6. Then you have to say that we will utilize the same. Okay, same. So same, this, that means we will add 0 padding to produce the same size feature map as the size of our image. Okay, so image size is M by M. So the feature map size will also be 6 by 6. Now we can think, we can also, another option we can have, that is called the valid. So valid means with no 0 padding. So we will not use the 0 padding. Kernel is restricted to traverse only within the image. So only within the image. That means we have already shown this one. So only within the image, and on that case, the feature map, the size of the feature map or output size of our convolution network will be M minus K plus 1. M minus K plus 1. And another option we have, that is called the full. So add 0 padding to the image enough to every pixel to be visited K times in each direction. And on that case, the size of the convolution operation, output size of the convolution operation will be M plus K minus 1. Okay, so these are the 3 options. So we have already shown the valid, I think, the convolution operation is performed in previous day. So this one, considering the straight equal 1 and filter equal 1. So at first, we have applied to this patch, and we got this 3. And then 1 bit shifting, because you can say straight is 1. So we have shifted this 1 bit. And considering this pass, again we generate another value, that is -1. And then we have shifted another bit. So this one is considered as a patch. And then apply our convolution operation, and we will get this 3. And then again we have to shift 1 bit. So that means we will get this one, this patch. Okay, and then apply the convolution operation, we will get this -1. So we will stop that is applying on convolution within the image. Okay, within the image. So next we have to just downshift 1 bit, and again we will get this one. And After right shift, we will get this one, and that one. Okay, so that means we are just applying the convolution operation utilizing this filter within the image. Okay, within the image without considering the zero padding. Then the feature map, the size of the feature map here we can see this is actually 4 by 4. Okay, but original image size is 6 by 6. But the size of our feature map is 4 by 4. So that means we have utilized here valid padding options. Okay, valid padding options. It means we will not utilize any zero padding. Okay, so the image size it will be m minus k plus 1. The feature map size, the size of the feature map, our output will be m minus k plus 1. So this is the feature map. Feature map we have, and the size is 4 by 4. Then how to compute that? So m minus k plus 1. So m minus k plus 1. So m is what? M is our image size. Okay, so this image is m times m. So here m is the dimension of our image. Then k, the k is the dimension of the filter. Okay, so here is the 3 by 3, 3 by 3. So this is actually the k by k, k by k. So m is the size of the image and k is the size of our filter. Then what will be the size of the feature map? Here it is m minus k. M is what? M is 6 minus k is what? K is 3, and then plus 1. Okay, plus 1. The size of our output size will be 6 minus 3 is 3 plus 1, that is 4. Okay, so equal 4. And we can see there is the output size here, 4 by 4. So this is how we can determine the output of our convolution. Okay, output of our convolution operation, considering the straight one. But we can see that if we think about our the convolution operation, but convolution operation considering the straight maybe instead of 1 we can consider a straight 2 or something. Uh, then for the valid convolution, with a straight s will result the output size is this one. Okay, so output size will be m minus k plus s divided by s. Okay, considering instead of just maybe s equal 1, if we consider s equal 2, then what will happen? Okay, so on that case, the output size will be this one, m minus k plus s divided by s. So m minus k plus s. That means if we apply on the same image, it will be like m is what? M is size of our image is 6 minus k. K is we have utilized the 3, and s is 2 if we consider 2. Okay, s is 2, and then we have to divide this one by 2 also. So then we will get what? So 5. Okay, 5 by 2. So that means 5 by 2 is 2.5. So 2.5. But if we can floor this one, then we will get the 2. Okay, so the size of our uh, output size of our feature map will be 2. Okay, so there will be no fraction because we don't have any fractional features. Okay, so it will be 2. So now another thing is how can we determine the output size of pooling feature maps? So for that, the output size of pooling will be for the pooling operation. So if we consider that the volume is this one, H1, D1, H1, W1, H1, and D1, then the after pooling operation, what will be the output? that. So here, okay. So what will be the output of our pooling operation? So H1, W1, H1, and T1. Considering this one, then output size will be W1 minus F divided by S plus 1. So what does it mean? It means that in case of our pooling, we have the feature maps, okay? Like we have one feature map is 4 by 4 feature maps, okay? And then if we consider our filter size is 2 by 2, okay? Filter size is 2 by 2, and a straight equal 2. This is the default for the pooling. So here is the straight equal 2. Then what will be the output of our feature map? The reduced feature map after applying the pooling operation. So here's the 4 by 4. It means our feature map, the size of the feature map is 4 by 4. So here we can see, if we consider the 4 by 4, then width. So this is 2D, okay, 2-dimensional. So we have just W and H. So that means in this case, we have the W is what? W here is 4, and F, that is the filter size. F is in this case we have utilized 2 by 2 filters. Okay, so F is 2, and a straight is also 2. A straight is also 2. Straight S is also 2. Then what will be the size of the feature map, reduced size of the feature map after applying pooling operation? It will be the new W, that is W2, is our previous W. Previous W is 4 minus the F. F is 2. F is 2 divided by the straight. A straight is also 2. Then plus 1. So here we can see 4 minus 2 is 4. 4 minus 2 is 2. 2 by 2 is 1. 1 plus 1, it will be 2. Okay. So the width of our reduced feature map will be 2. Similarly, the height also, okay, but in our feature maps, we have considered the feature map is 4 by 4. So width and height will be the same for that case, okay. So in this case, the height will also be the same, 2. So that means the feature maps, we can see we got the feature map. What is that? Here, yeah. This is the reduced feature map. The size of that is 2 by 2. Okay? So here is 2 by 2. This one is also 2 by 2. 2 by 2. Okay, considering our max pooling of filter size 2 by 2 and a straight 2. So this is how we can find out the output of the pooling layer also. Okay. So now I think you understand how to calculate the output size of our convolution operation and how to calculate the output size of pooling operation. Okay, output size of pooling operation. And then now we want to find out the total number of parameters necessary to update, okay, or necessary for training. So that is the learning parameters. How to calculate the total number of learning parameters. So on that case, we have to know that is the output size, and then from the output size we can calculate. Like if we consider that we have this input, the input size is 1, 28, and 28. Then after applying our convolution operation, the convolution operation, how many filters we have designed, and what's our convolution filter size. So here we can see this is the input. Input is 1, 28, and 28, and the convolution we have added, it is 3 by 3 filter we have added, and how many filters we have added? That is 25 filters. Okay, 25 filters. So that means here we have utilized 3 by 3 filters and 25 filters for that. Then what will be the output size after this convolution operation? So we can see that is for that case, we have utilized, that is our, okay, 3 by 3, 25, and consider that that is the straight equal 1. Okay? That means if we apply the valid convolution, the valid padding, apply valid padding, the output size will be m minus k plus 1. So what's the image size? The image size is 28 by 28. So here is m is 28. What's the kernel size? Kernel is 3 by 3. So 3 plus 1. We can see 28 minus 3 is 25. 25 plus 1 is 26. So 26. The output size of this convolution will be, here is the 26 by 26. Okay, 26 by 26. This is the output size of each and every feature map. But how many feature map it will create? So how many filters we have applied? 25 filters we have applied. So that means it will create 25 feature maps. Okay, that's why here is the 25 times 26 times 26. Okay, then apply the max pooling. Considering our 2 by 2 filter and straight equal to. So on that case, what will be the that is output of the pooling? So here it will be the W minus F divided by S plus 1. Okay, in this case we can see it is W. W is what? W is this one. And the feature map size is 26 minus what is our F? F, this one is F. In max pooling we have utilized 2 by 2. Okay, so that means the feature map size is 2. And what is our S? S state is 2 plus 1. It means 26 minus 2 is 24. 24 by 2, so it is 12. 12 plus 1 is 30. Okay? So here is the 30. Here is the 30. And then how many feature maps we have? 25. So that means after reducing the size of the feature map, we will get the same number of feature maps. Just size will be reduced for each and every one. And then again apply the convolution operation. But this time the convolution filter we have utilized the 3 by 3 convolution. And how many filters we have added? The 50 filters. If we can remember this one, you can see here 53 by 3. Okay, 53 by 3. So 3 by 3 and 50. Now that is m minus k plus 1. So m is what? Now we can see m, in this case m is 13. M is 13. And minus k. K is what? K is our filter size, is 3. M minus k plus 1. Okay, so here is m minus k plus 1. Then the straight is 1, considering straight 1, the valid padding. So in this case, 10 plus 1 is 11. 11. We can see here it's 11. Okay, 11. Then after that, we have to apply the max pooling. Then what will be the output size of that, of the pooling? And it will be W minus F divided by S. So W for this case, the W is 11. So W is 11. And then the filter size, we have utilized 2 by 2 filter size. with a straight 2, is equal to, so that means W minus F is 2, then we have to divide it by 2 plus 1. It means is 9. So here is a 9 by 2. 9 by 2 is 4.5 plus 1. So here is floating. So this is 4 plus 1 equal 5. So here is the 5. 5 by 5. But again, we have utilized 50 filters. So the number of the reduced feature map will be the same. There is a 50, but the size will be reduced from 11 to 5 now. And now we have to apply the flattening. Okay? So that means how many feature maps we have? Here is 50 feature maps. And here is the size of the feature maps are 5 by 5. So if we convert it to one dimension, then how many elements we will get? So it will be 50 times 5 by 5. That means 50 times 25. 50 times 25. It will be 0 here, and 5 times 25 is 125. So here is 1250. 1250. Okay, 1250. So after that, we have to think about our neural networks, the fully connected neural networks. That means in this layer, we will have 1250 neurons. And according to this design, in our hidden layer, we have 100 neurons. And then in our output layer, we have 10 neurons. Okay, then I think we know how to calculate, that is the number of parameters necessary for this neural network. Okay, then then the last thing we want to find out, that is the number of parameters. The number of parameters. So now, number of parameters to learn, or usually we call is learning parameters. In many times, you will heard that, okay, the number of training parameters for this model is 16.7 billion. Okay, it means that learning parameters for that model is 16.7 billion. Specifically, the large language models, those have huge number of parameters to learn. But how to calculate that? If we consider about this CNN network, a convolutional neural network, then how to calculate the number of parameters for this case? Okay, so in this case, specifically the learning parameters of convolutional neural networks are the filters. If we consider our 3 by 3 filters, that means in training time, it will update the values of the filters. Okay, values of the filters. That's why we need to consider the filters. So here, how many parameters for each filter? So we can see at first we have utilized 3 by 3 filter. So 3 by 3 filters. So that means how many parameters for each filter? For each filter, how many filters we have added here? 25 filters. But for each filter, how many parameters there? 3 times 3 is 9. So that's why how many parameters for each filter? Here is 9. The number of parameters is 9 for each filter. Okay, so if it is asked that is the total number of how many total number of parameters here in this convolution, then what we have to do? For each filter, we need the 9 parameters, but we have total 25 filters. The total number of parameters on that case 9 times 25. So here in this case, for each filter, we have 9 parameters, but we have 25 filters. That means the number of parameters we learned here 9 times 25. The max pooling, actually in pooling layer, there is nothing to learn. It will just reduce the size of our feature maps. So that's why there is no learning competition in that case. We have another convolution layer. Another convolution layer. And we can see in this convolution layer, the input size is this one. This is the input. This is the input. So that means we can see we have 13 by 13 size feature map. And how many feature maps we have? Like that. 25 feature maps we have like that. But in this case, the input, if we can consider input, then what's the image size? 28 by 28. This is the input image size. And how many images like that? Just only one image. One image, because you can see this is the grayscale image. Okay, grayscale image. Okay. So now for this convolution, then how many parameters for each field? How many parameters for each field? Here in this convolution, we can see the filter we have used 3 by 3, and this type how many filters we have utilized here? 50 filters. 50 filters. But each filter will actually work on 25 images. Okay, 25 feature maps. 25 feature maps. So the how many parameters for each filter? So each filter will we can see the parameter will be for each filter it will be 9 times 25. So here is 25, but previously we have just only 1. Okay, so here is the 25. That means 25 planes are there. So that's why that is the how many parameters for each filter. For each filter, we can see each filter is 3 by 3, but we have the input size is 25. So that's why the total the number of parameters for each filter will be 25 times 9. 25 times 9. So that means 225. 225. Now, if we ask the total number of filters here, the total number of filters, then we have to multiply this one by 50 because we have considered 50 like filters. Okay, so that means the number of parameters will be 225 times 50. Okay, so the number of parameters to learn for this convolution. Now, after that, the pooling layer is there. In this pooling layer, we have that means the number of there is nothing to learn here. It will reduce the size of the feature map, so no parameters actually necessary in this case. Okay, now we have to think about our fully connected part. So this part, there is how many parameters to learn in this case. So the input size in this case, input size is 1250. So here is the 1250. Input size is 1250. Then the hidden layer size is 100. Okay, so that means total number of connection is 1250 times 100. 1250 times 100, the total number of connections. Okay, fully connected. Not only the weight, but we have to think about the bias also. How many biases we have to add here? And for each and every hidden neuron, we have to add one bias. So that means we have to add 100. Okay, this is for our input layer to hidden layer. Then next we have to consider plus the hidden layer to output layer. The hidden layer to output layer. In hidden layer, how many neurons in hidden layer? So total 100 neurons times how many neurons in output layer? 10 neurons plus the bias. We have to consider the bias for each and every neuron of output layer. So that means plus 10. So that means the number of parameters in this fully connected neural network, it will be 1250 times 100 plus 100 plus of 100 times 10 plus 10. So for the fully connected neural networks. And then we have to add this, there is the plus 225 times 50 plus 9 times 25. So if we add all this, then we will get the number of parameters to learn here in convolutional neural networks. So this is how we calculate the number of parameters. So I think that's all in our convolutional neural network lecture. So if you have any question, then you can ask.
স্যার আমাদের এখানে ম্যাক্স কুইন থেকে কনভলিউশন লেয়ারে স্যার ফিচার 25 থেকে 50 কিভাবে হলো?
আবার বলো তো কোশ্চেনটা।
স্যার আমাদের স্যার ম্যাক্স কুইন থেকে কনভলিউশনে যখন স্যার আমরা গেছিলাম স্যার তখন স্যার আমাদের ফিচারটা স্যার 25 থেকে স্যার 50 হয়ে গেছে, এটা স্যার কিভাবে হলো?
আচ্ছা, এটা 25 থেকে 50।
ইয়েস স্যার।
এখানে দেখো, যখন আমরা ডিজাইন করছি নেটওয়ার্কটা, তখনই আলটিমেটলি মানে প্রত্যেক লেয়ারে কতটা করে ফিল্টার ইউজ করব সেটা বলে দিছি। যেমন এই কনভলিউশন লেয়ারে আমরা ফিল্টার ইউজ করব কতটা, 25টা ফিল্টার ইউজ করবো। পরের কনভলিউশন যখন নিচ্ছি তখন হচ্ছে আমরা ইউজ করবো ফিল্টার কতটা, 50টা ফিল্টার ইউজ করবো। এটা ইউজার ডিফাইন, ঠিক না? তুমি যতটা চাও ততটা ফিল্টার ইউজ করতে পারো।
ওকে স্যার।
তো সেজন্য প্রত্যেকটা কনভলিউশনে কতটা ফিল্টার থাকবে এটা ইউজার ডিফাইন, ইউজারকে বলে দিতে হবে।
থ্যাংক ইউ স্যার।
ওকে, any other question? Okay, so I hope you understand. In our next class, I think I will take the physical class there, okay, in person class. So